In this video, we're going to discuss how to normalize a wave function. We're going to use the particle on line wave function as an example. Okay, so if the wave function squared is going to be the probability density, then the integral of the probability density equals 1. All right. Now the first thing we have to realize is that this wave function that we say sine of n pi x over L, it's only sine between 0 and L. So we don't integrate over all space for that functional form. What we do have to do is integrate over all space for psi equals 0 and psi equals 0. However, the integral 0 is 0, so we don't actually have to write down that integral and do it and find out if it's 0. All right, so in the particle on line problem, the functional form in the middle has to, first of all, match psi, has to have a magnitude of 0 in order to be continuous with these other two parts. And the square integration must equal to 1. All right, so this is true for pretty much any normalization. You write psi squared, whatever it is, you integrate over whatever range you have to integrate and set it equal to 1. All right, so we're integrating over x. All right, and so now we're going to multiply the function by a constant, okay? So if I was just to do this without n, the integral won't be 1. It'll be some other number. However, I can find out what number I need to multiply by so the integral does become 1. All right, so once you write down n times the functional form that you have, square that, put it in the integral, solve it, and then solve for n. Okay, so what this boils down to is being able to do some integrals. All right, so integral from 0 to L of n squared. Again, we use the vertical bar just in case we have complex functions. If you don't, it's just simply the square. All right, sine squared of n pi x over L dx. Set that equal to 1. All right, so this involves doing the integral of sine squared. Now, there's a couple of different ways to do this. One's by substitution, one's by looking up an integral table. All right, so I'm going to use a trick that you don't necessarily need to know how to do for this problem, is that sine squared is equal to 1/2 minus 1/2 cosine of 2 theta. Okay, so I'm going to use a trig substitution, and that's going to be it. All right, so notice that there's a 1/2, so I'm going to put the 1/2 and the n squared outside the integral range, 0 to L. All right, now of 1, or dx, and then minus integral from 0 to L of the cosine of the double angle, which is 2n pi x over L dx. All that's going to be equal to 1. Okay, so that's all we did, was we did a little trig substitution. So what's the integral of it dx? Well, it's x. So this is x from 0 to L times 1/2 n squared. All right. All right, now, what's the integral of cosine? Sine. Now, with this constant multiplied times it, we have to account for the fact that if we were to take the derivative of this sine function, we're going to get an L and a 2 and an n and a pi. So we actually have to put that in here. All right. So that's actually a constant. So this looks like it's part of the argument. It's not. So let's do it this way. minus this times sine of the double angle, 2n pi x over L. All right, now this is from 0 to L as well. And all that's equal to 1. Okay, so looks complicated. All right, well, what is the sign of this term here? Well, for x equal to L, you get the sign of a multiple of 2 pi. So what is the sign of 0? 0. What's the sign of 2 pi? It's 0. So any multiple of 2 pi, the sign is going to be 0. So this first term is 0. What about the sign of when x equals L, you get the sign of 0, it's also 0. So both of these terms, when x equals 0 and x equals L, are both 0. So actually the integral is very simple. It's just x from 0 to L. And x from 0 to L is just L. All right, so all of this boils down to a very simple equation. 1/2 n squared times L equals 1. All right, so L is the length of the box. N is the number we're solving for. So we have to solve for n. All right, and so n squared equals 2 over L. All right, now this is the big thing you're going to see about normalization. Since you always get n squared, you're always going to be taking the square root. And so if you see a square root of a number times a function, it's been normalized pretty much most of the time. All right, now the other thing to remember is when you take a square root, you get two roots. You get the plus one and the minus one. But the magnitude of the coefficient doesn't matter in quantum mechanics because remember the probability is equal to the coefficient squared. So the positive root squared or the negative root squared is going to give you the same probability.